So 6.3, sampling distributions and estimators. So here are some definitions of things you have already seen in the previous chapters. So population, if you want to shorthand this, maybe not write all of it, but just in your own words, that's okay too. But a population would be all individuals. Sample would just be a sub-collection or a part of it. Parameter goes with population, statistic goes with sample. And the last thing is sampling variability, which just means when you take a sample, if everyone took a different sample in here and gathered the same or asked the same question, you would all get different answers because it comes from different samples. Okay, these are the symbols that we have used. We haven't talked a whole lot about P and P hat. So when we talk about proportions, that's with all categorical data. So when I say proportion, I'm just saying like part over whole, which we'll take some proportions in here. You've seen it before, I just don't think I've used these terms. But if I said 56 out of 100 people answered yes to this question, that's a proportion. For sample, it's P hat. And then for mean, X bar, make sure that you put a bar over the X, and then mu, then standard deviation, sigma, and S. You might want to write in, I typed this in, but categorical, numerical, numerical. So when I say the word proportion, that goes with categorical data. Mean and standard deviation go with numerical. So when I say the word sampling distribution of a statistic, a sampling distribution is formally the distribution of all values of the statistic when all possible samples of the same size are taken from the same population. So imagine, this is just kind of an example or a scenario. Imagine all PCA is my population, so 520 about people at the school. If I were to pair every single person, so you yourself are paired with everyone at the school, that would be an example of the sampling distribution. So pairs of 2, every single person gets paired with everyone. That would be a huge number of options, right? If everyone could get paired with everyone else. I listed out all the pairs. That would be a sampling distribution.
Are we writing the sample?
Yes.
All of it?
Yeah.
That's a lot.
A lot of pairs. Even just in here, if we paired everyone in here, that would be a lot of pairs.
How many pairs do you think there would end up being?
We could figure
Is
it
there a
out.
formula for that?
That is in the
Why
problem.
did you look at the evil and you're like, oh,
We're not gonna get into. We won't ever deal with numbers that big. So we are going to create sampling distributions, but the population will be really tiny, like 3 or 4, because then we'll list out all the possible pairs.
Oh, this was like on Alex when they used to be like, Johnny can wear a red shirt,
Yeah.
a green shirt.
That's exactly what it is. So
and
it's
has black pants and
so
white.
what you did in whatever grade, middle school, you actually created a sampling distribution from that.
I like it.
They were so hard.
Isn't it just like multiplication? Don't you just multiply them together? So like if you have 5 options and 2 options, then you 5 times 2, you get 10 options. 10.
So why do we do this? This is kind of seems redundant. Like when we have all 520, why would we pair everyone with everyone? What's the purpose? So, question I'm going to ask you.
No.
Go back. Okay, then we won't ask the question because we're waiting. All right, raise of hands. How many of you feel comfortable in a self-driving car?
I've never done it.
I haven't either. Would you feel comfortable?
Control.
Yeah.
I like
You would let like a machine, a car.
Yeah.
Yeah.
Like 100% safe.
I mean, no, definitely.
Yeah. Is anything 100%
I feel like it's safe. But it's not like 100%
Yes.
Calm down.
Thank
calm
you.
down.
Thank you.
We're
So,
just
a
gonna-
national survey was done, and 70% of all adults among the population
Is this on?
do not feel comfortable. This is not on your notes. Do not feel comfortable in a self-driving vehicle. In a TE connectivity survey of 1,000 adults, 69% said they don't feel comfortable. Why are these numbers different?
It's not really
Because
different.
it's
They're
the
not
population, or the sample that they picked.
So it's just the sample of 1,000 people, right? So sample of 1,000 people is equal to 69%, but the population is exactly 70. So within each sample, you're not going to necessarily get exactly 70 if you're taking a sample just from the population. It won't always equal that. And that goes back to our vocab term sampling variability. So every sample is going to vary a little bit, but what a sampling distribution does is it averages out every single possible sample, every single possible combination, and it ends up being 70%. So here, what they did is they assigned 50,000 people to go out and take samples of 1,000. So how many people is that? Somebody in their calculator, or just what do you think that be? Whatever 50,000 plus 3 extra zeros are.
5 million.
Oh,
50 million.
50 million. 50 million people,
That's not a lot.
right? That's a lot. So 50,000 people took surveys of 1,000 people. That's 50 million people. Then they came back and they reported their results. So they took their average of 1,000 and they made a graph. So this graph right here represents 50,000 percentages. Like the 50,000 people. Some got 68%, some got 72%, some got 70%. And if you can see this, what characteristics do you notice about this graph?
It's bell shaped.
It's bell-shaped, so it's a normal distribution,
Good work.
and it's centered at
0.7.
0.7,
70%.
which in the beginning was the population mean. So, the whole reason of why we do this, I wish I had a cooler answer for you. Like it changed the world or something, and maybe it does. But the answer that I give you is why do we do this is so that we can take just a number like that 70%, and we can build a normal distribution around it and answer questions. Like, you know how in the past we've answered questions using normal distributions. Like, what is the percentage of people between 68 and 72? And you have used normal CDF in your calculator. So taking a number and building a normal distribution around it to answer questions. That is why we have a sampling distribution.
I feel like you tried to make that sound cool and meaningful. It just
I feel like
But if I just told you the reason why we do it is to make a normal distribution, you may not have remembered. But
that's a good point. Now I'm gonna remember it.
remember the self-driving survey.
I'm just gonna.
No.
Okay, the sampling so we're going to find two types of sampling distributions, mean and proportion. So this is split into two.
Now we know her favorite student. Her name's up there twice.
Ouch. She doesn't actually like me.
You're
It's
right.
fine.
I wrote it twice on purpose. And what if your name shows up? Singe.
That'd be scary.
It might be. So go ahead and write down the definition, and then I'll explain it. How did I describe what a sampling distribution was originally? Don't use fancy terms, just explain it.
Wait, what'd you say?
What did I say a sampling distribution was? All the possible pairs.
Combos.
Okay, sampling distribution of a mean is all the possible pairs, but then actually calculating the average within each pair. So, remember our example, all 520 PCA students. You are paired with every person at PCA. That's a lot of pairs,
Are we
right?
including teachers or no?
No, just students. So, from that, within each pair, imagine, so I just picked two people, Miranda and Julia. I'm going to calculate your average GPA. Then Miranda and Molly Claire, their average GPA. It's going to be different within each pair. So their two average GPAs and those average GPAs are different. Every pair is going to be different. Then take all those averages, like all thousands and thousands and thousands of them. I average that number together, and that becomes the population mean. That's a lot of work, right, to do that because I already know the population mean. I could just go to the guidance office and do that.
But it's okay.
Figure that
Our
out.
Computers do it for us.
Exactly. And then I can answer normal distribution questions on that. Like from there, once I have my normal distribution that's centered at 2.6, I don't know, I just made that up. Maybe that's my population. From there, I could say what percentage of PCA has a GPA between 2.0 and 3.0. So that's why I build a sampling distribution, so I can answer those questions. Two things I do want you to write down. The population mean will always equal the sampling distribution mean. Always, always. So today we're going to go through the long way. Just write it at the bottom of your paper or something. So we're going to go through the long way today, but then I'm going to show you a shortcut next class. You have to learn both of the ways.
No.
You don't have to, but you might make a bad grade. So you have to know both of them.
Was that a threat missile?
That's a problem.
What did I get on my test?
I don't know.
You think
Are
I
they
did?
graded?
No.
You think I did good, bro?
So, sampling distribution of proportions. Same pairs of people. Remember, thousands and thousands of pairs. But instead of calculating their average GPA, I'm going to use categorical data. So I'm going to count how many girls are in the pair. If all of them are boys, then that's 0%. So Cinque and Peyton, 2 boys, 0% girl. Yes. Peyton and Tatum, 50%, 1/2. Tatum is a girl. Tatum and Lindsay, 100% girl. So then I would average like 0.5 and then 1. 100%
So if you
is
had
1.
a guy and a transgender, would that be 25%? Should we not be one teacher?
That's super funny.
It is.
Then if I took all those averages, then I would find out the actual proportion. Like, does anyone know what the ratio is? Like, what percentage of girls?
Or guy.
In the world?
No, at PCA.
We could just do this
Like
live.
80%. Like
Girl?
way more girls than
No,
guys.
there
No.
are way more guys. If there's like 40 girls in our grade, I would like
Probably,
one
like, in reality, it's probably
But
like
like the
60,
other
40.
grades.
I bet so. Okay, so population proportion. However many girls, percentage of girls at PCA would always equal the sampling distribution.
What you just do?
Then
Yeah, is it
the
relevant?
sampling distribution will always be normally distributed. Yeah, or you can just say same as what you did for the means because you've already written this before. Here's a visual of what sampling distributions look like. So all of these little like p hats are all the possible pairs of people. All the possible pairs, all the samples, and they all create a bell shape, a normal distribution. Same with means. All of the little sample means
X bar.
create normal distribution.
Do they?
So the purpose of a sampling distribution is to take a number and create a normal distribution out of it because you can't do anything with just one number. So you have to repeat that sample over and over and over and over thousands of times or as many times as possible to get that bell shape. Okay, next word is estimator. An estimator is a statistic used to infer or estimate the population parameter.
Do we need to write that down?
So basically, an estimator is going from sample to population. That's the goal. So I want to go from a value I have in a sample, I want to estimate the population from that. An unbiased means that they're equal to each other. If I said that something were biased, then they would not equal.
What is it? So like the 69% to 70%? That would be biased.
Well, no, because just an individual sample in itself does not have to equal it, but all of the samples possible have to equal it. So proportion, mean, and variance will always be unbiased if you gather any of those 3 sets of data. median, range, and standard deviation are biased. So I'm not going to ask you to do anything with these other than knowing that unbiased, proportion, mean, variance, and biased, median, range, standard deviation. So you need to know which is which. But I'm only going to ask you to calculate mean and proportion. And we're going to do those together.
Ooh, we're gonna go to practice, bro. I love statistics.
I know.
Is this our homework too?
No, homework's on my math lab. Okay, here we have a friend of the author has 3 children with ages 4, 5, and 9. Let's consider the population consisting of 4, 5, and 9. If the 2 ages are randomly selected with the replacement, identify the sampling distribution of the sample mean by creating a table representing the probability. And so we're going to do all that together. Then it says, do the values of the sample mean target the value of the population mean? The answer is yes, because mean is a unbiased estimator, but we're going to prove how. Okay, so let's actually find what is the mean of the 3 ages. 4, 5, and 9.
Nine.
9.
No, divided by 3.
9 divided
4
by
plus
6.
5 plus 9 divided by 3.
6.
6. So you're going to need your calculator for this. We're not going to make any lists or anything like that, but you will need it maybe to find averages. So population mean is 6. Now let's create a sampling distribution from that. So what are all the possible combinations? And remember that it's with replacement. So if I pick the 4-year-old out, it goes back. I can pick it again. So I can have 4 and 4
Oh. So 6.
because it's with replacement.
6.
Then I can have 4 and 5,
4 and 9.
4 and 9,
And then 5 and 5.
5, 4, 5, 5, 5, 9,
Oh.
9, 4, 9, 5, 9, 9. It won't be more than usually 4 or 5.
We would be here forever.
Yes. So we're keeping the population small for that fact.
9.
Now, I want to calculate the average age between those numbers. So the average age of 4 and 4 is 4. Average of 4 and 5 is 4.5. Average of 4 and 9, 6.5. Good. 5, 7. Mhm.
I think the average mean is 6.5.
So here's all the possible combinations and their averages. It wants us to create a table. So my table is average age and then probability. So I'm going to go and I'm going to list all of my average ages. And you don't need to list the repeats twice. You only need to list them once. So we have 4, 4.5,
8.5.
5, 6.5, 7, and 9.
4.
Now we're going to look at the probability. So how many total options are there?
9.
There are 9, so all of this is out of 9. So 4, I'm going to cross them off as I go. So 4 occurs 1 out of 9 times. 4.5, 2 out of 9. 5, 1/9. 6.5, 2/9. 7, 1/9. 9. Oh, twice. Sorry. 2/9, and then 1/9. Now I'm going to calculate the average. To do so, in my calculator, I'm going to take, so I'm going to write this out, but you don't have to write out your steps. You can just do it in your calculator. So follow along with me in your calculator. 4 times 1/9 plus 4.5 times 2/9, and so on all the way. So plus 5 1/9 plus 6.5.
Whoa. Way too
Is there an Asian word for this?
There's a couple of options of things you could do. I can show you your different options.
This is gonna take so long on my math lab.
Oh,
They're gonna give us like 40 options.
But here's the thing, what should it probably equal? 6. You might, to check your work, you can show that it's 6, but if you want to just take a guess and take a risk, then just say it equals 6.
I'm a risky guy.
Well, if you know it's unbiased, and you can probably assume it's going to be 6.
Mm-hmm. So I would say mu, and then my subscript is x bar. So it's not just mu, it's going to have a subscript of an x bar. That's the mean of the sampling distribution, is what that means. So in this case, population mean equals sampling distribution mean. So it is an unbiased estimator. We just proved our point.
So what's the answer out of all that?
Yes.
We just proved that it was unbiased. This is kind of like a proof.
I don't like that word.
Okay, what I want you to do now is try number 2. You can try it with the person next to you. So, step 1, listing out all of the combos. Step 2, calculating the average. 3, make a table.
This one is more.
Still typing.
So at least my math lab is going to kill me. It's gonna be a fault.
There are not very many questions on my math lab, so I think like 2 or 3 that you have to do this out. And then some are just vocab questions.
That's so nice. You pick.
Okay, next page.
I got
So we're gonna-
640,000.
We're going to look at proportions now. So consider rolling a die. We're going to measure or count the proportions of odd numbers. So automatically, proportions of odd numbers in a die is what?
1 out of 6. 3 out of 6.
1, 3, and 6, which would be 1/2, so 0.5. So P equals 0.5, not mu, because P is proportion. 3 out of 6 is 1/2. And so we're going to list out, so if I'm rolling rolling a die twice, then I'm going to list out all of the options. So I could roll a 1 and a 1, 1, 2. So I want you to list out all of the options first. Okay, from here, I'm going to count how many of them, or the proportion of odd within each pair. So, like 1 and 1, both of them are odd, so that gets a 1 next to it, 100%. But 1 and 2 would only be 50% odd, so 0.5. And then if none of them are odd, what would go next to it? A 0. So it's either going to be 1, 0.5, or 0. So go through and list 1.5 or 0. Okay, from here, I'm going to list out what are my options. 0, 0.5, and then 1. And there's 36 total options, so out of 36. So count all the zeros. So you should get 9 out of 36, which reduces to 1/4. So on the My Math Lab, make sure you reduce your fractions. So I don't know if it'll count it wrong or not.
It's gonna be a lot of halves. Yeah. Yeah. There's 3 on every row.
And then if you find we're going to call this the mean of the sample proportions. So mu of p hat. So you can either put them in the 2 lists like we just did for the last example, calculate the average, or you could say 0 times 0.25 plus 0.5 times 0.5 plus 1 times 0.25. So you're multiplying across, adding down. Either one, they both will get you the same answer, but you get your sampling distribution mean equals 0.5, which is the same. Population equals sampling distribution, so it's unbiased. Mhm.
If you have the same amount of zeros and ones, they would balance each other out to average 0.5.
Yep. Yes. So we assume anytime we're talking about births, I don't know all of the science behind it, but we do assume that it is 50-50 chance of having a boy or girl.
No.
I know there are tons of other factors and things that go into that. However, we assume in statistics that it is a 50-50 chance. So when I'm having 2 children, it could either be boy, boy,
Boy, girl.
boy, girl, girl, boy, girl, girl. We're not
GG.
counting twins.
GG.
We're not counting any of that. Just 2 children. And I want to count the proportion of girls within each scenario. So I have 0, 0.5, 0.5, and 1. And what do those average to be?
50.
0.5. And the original is also 0.5. They match, so that means it's unbiased.
Whoa.
If you were to make the table 0, 0.5, and 1, the same table. So average and then probability. Because on my math lab it wants you to make that table.
Well, my bad.
So now for number 5, try it with 3 children. We're going to have a few more options with 3 children. Okay, from here, calculate the proportions.
Oh.
0, 1, 3, 0, 0, 2, 5, 6, 1, 5. Go for it. Flat. Tango Blue Alpha Dolphins. 10-4.
Just be getting all willy-nilly out here.
Bravo. Where's the JJ?
Yeah. Yeah, so when you find the average, you get 0.5. The average of boy or girl, always 0.5.
Sounds like
Okay, homework is 6.3, My Math Lab. You might be able to get it done. There are 6 questions.